All right, so the other day we were talking about just uniform circular motion, and we said that for something to travel at a constant speed in a circle, it has to always be accelerating, okay? Which means there had to always be a force that was pulling it towards the center. It doesn't actually get closer to the center, but it accelerates towards it, changing its velocity all the time, making it travel in a circular path. Okay, that sort of ring a bell for everybody from Monday? Okay, so what we want to look at today is more now the forces that can act as centripetal forces, okay, those center-seeking forces that keep something moving in a circle, how they work, okay, and then some of the basic formula type stuff that we're going to have to do in order to solve problems related to centripetal force. Okay, so circular motion cannot occur without a force pulling into the center. That's what we talked about the other day, kind of our introduction to that. Okay, many forces can act as a centripetal force. Okay, we talked about a few of those the other day. Friction can act as a centripetal force, gravity, tension in a rope, or whatever happens to be. Okay, centripetal forces all operate the same. That is, they push or pull, most of the time pull, an object towards the center of a circle. Okay. So we're going to look at also now some applications. We're going to look at how banked curves use Newton's third law to produce greater centripetal force. Okay, so a bank curve is like the exit or the on-ramp out here getting onto Highway 2. Okay, that road is banked slightly, okay, in order to give us greater safety when negotiating the corner in poor road conditions. If you have ever watched like NASCAR, okay, or they just have like the one big circular track, okay, the walls are banked incredibly steep. Okay, like so steep that when they pave them, the paving machine has to be held on the corner by a crane. Okay, because they're that steep. Right, that is how the cars can take those corners at the breakneck speeds that they travel at. All right, so Newton's second law tells us that whenever an object accelerates, there has to be a force present to do that. Okay, so it says that F net equals mass times acceleration. On Monday, we learned that centripetal acceleration is equal to v squared over r. Okay, that was one of the formulas that we learned on Monday. So if we're talking about centripetal acceleration, okay, and centripetal force is the net force of all the forces acting on an object moving in a circle. So it is then the net force. So really, all we're saying here is that it is mass times centripetal acceleration, which is mv squared over r. I'm just substituting this in for this. That will be our most fundamental formula in this unit. Centripetal force is mass times centripetal acceleration, mv squared over r. Okay, we will use that as often as we used m times a in the last unit. Okay, so we use it all the time. That said, sum of all forces in this unit is a lot easier than sum of all forces in the last unit, because there's not going to be like vectors and stuff like that. It's either into the circle or out of the circle. It's pretty easy. Okay, it's just plus and minus. There's never going to be any like vector diagrams or anything like that. Okay, so it's going to be a lot easier in that respect. Okay, so that's what we're saying right here. Okay, so the net force for an object moving into the circle, or sorry, moving in a circle, always has to be into the center, thus the centripetal force. All right, in lots of cases, identifying the centripetal force is easy, especially if the object's actually physically connected to something, right? But in some cases, it's a little harder to identify at first look. Okay, when something turns a corner sharply, there's nothing connecting it to the center of the corner. Okay, but something keeps it in that turn. Okay, what is it? What keeps you from sliding when you turn a corner? Friction, yeah, static friction specifically. Okay? If you drift a corner, then it would be kinetic friction, right? Because you actually change the direction of the car and make the wheels spin, and the spinning wheels actually pushes the car towards the center. Okay? Static friction is actually greater. Okay? You can take a corner much faster without drifting it than you can drifting it. Oh, it's true. It's absolutely true. Okay? And here's the thing, guys. I watched Mythbusters do this. They built a track with a bunch of corners, and they took it in just like a beat up old like Crown Vic, okay? And they did all the corners without skidding, as best they could, no drifting. They took all the corners and timed themselves. Both Jamie and Adam did it. Then they brought in the Drift King, the guy from Japan who started it all, and they had him do the course. And he could not beat their times when they were not drifting. Okay? And it wasn't like a small difference either. He lost significantly each time. Okay? The reason being is, in order to set up the drift, you actually have to go wider and actually slow down a little bit to set the drift up. So the drift actually doesn't allow you to go the corner faster. It can help you negotiate sharper corners sometimes. Okay? But in terms of speed, not drifting a corner is faster. It's why you never see Formula One racers drift a corner during a race. Okay? It's just not faster to do it that way. Oh, I'm not saying it's more. I agree with you 100% in that drifting the corner would be vast amounts of fun compared to not. Oh. Oh, okay. Well, we're not factoring in the fun factor here. Believe me, it's fun and it looks cool. Okay, believe me, going around a corner without spinning the tires does not look nearly as cool as a big cloud of blue smoke, okay, trailing around the corner. But it's just, I'm telling you, it's faster to do it the other way. All right. So we want to look at a couple of things here. Okay, we know the formula for centripetal force is mass times speed squared over r. Okay, now if speed is squared, which has a bigger effect on the centripetal force, mass or speed? Speed, because speed has an exponential relationship. If I double the mass and keep the speed the same, centripetal force doubles. If I keep the mass the same and double the speed, centripetal force will quadruple. Okay, similarly, the relationship between radius and centripetal force says that if I make radius bigger, the centripetal force will go down because I'll be dividing by a bigger number. Everybody okay with that? Okay. Now, if I make both the speed and the radius bigger, will this force get bigger or smaller? Yeah. Okay. It's still going to get bigger, right? Because again, speed has an exponential relationship with centripetal force, whereas radius, it's only linear. Okay, so if I was to double them both, okay, this speed would still essentially double. Or sorry, the centripetal force would still essentially double because they would cancel a little bit here. Okay, everybody kind of follow there. Right. So that goes to the merry-go-round thing that we were watching the other day. Okay, in the center of the merry-go-round, what's my radius? I'm standing right in the middle. 0. So how much centripetal force is required to keep me moving in a circle in the middle of the circle? None. I'm standing in the middle. I have no radius. I'm really just spinning around as opposed to orbiting something. Okay. The further out I go, okay, according to this formula, as radius gets bigger, centripetal force gets smaller. But the further out I go on this merry-go-round, the faster I'm going as well. Okay. We talked about that, how it takes the same amount of time to go around this part of the circle as it does this part of the circle, as it does this part of the circle. Okay? So if it takes me the same amount of time and I'm going around a circle this big, I'm definitely going faster. Right? I'm always going faster on the outside of the circle. Okay? So radius is increasing, but so is speed, and speed has a bigger effect on centripetal force than radius does. So the further out in the circle you get, okay, the more centripetal force would be required. That's the whole idea behind kind of like black holes, right? If something gets down near the event horizon, it would be going so fast that it would be going fast or as close to the speed of light as possible, right? It would be accelerated to that, especially if it was orbiting. Okay, so let's do this problem here. So we have a model airplane that is 0.9 kilograms and it's moving at a constant speed. Find the tension in the string for speeds of 19 meters per second and 38 meters per second on a 17-meter line. So they're telling us the radius is 17 meters, find it at 19 meters per second and 38 meters per second. All right. So we have mass times speed squared divided by the radius. All right, so we got 15.3 meters per, or sorry, newtons, 15.3 newtons. Oh, can't use black, that doesn't show up. 15.3 newtons. Everybody okay with that? All right, now we're going to do the same thing for when it's traveling at 38 meters per second, which is twice as fast. So predict, what should this number be? 4 times bigger, yeah. All right, so it should be like 46 point something. Whoop, what did I do wrong there? Oh, I went divided. 0.9 times 38 squared. Sorry, 76, 46, 76. Okay. Did I mess something up on that first one? I think I did. Let me check that first one again. Yeah, that's better. Okay, now it works. So this should be 19.1. I must have typed something in wrong here. All right, so this one's 19.1. This one is 76 point. Oh, no, you don't have it. Oh, 76.44. Okay, so that's exactly 4 times bigger, right? Okay, so we know then that speed has an exponential relationship on centripetal force. Okay, mass would have a linear relationship. If I swung twice as much mass around in the circle, then I would need twice as much force. I mean, think about it. To hold something heavier in a circle, you have to pull harder. Okay. All right. Now, the effective radius on centripetal force should be inverse. The bigger the radius, the smaller the centripetal force required to keep it in, provided the speed remains the same. Okay. All right. So the rock in the figure has a speed of 28 meters per second and a mass of 0.9 kilograms. Find the tension in the lines, that's the centripetal force, for 11 meter radius and a 22 meter radius. Okay, so again, Fc equals mass, so 0.9 times 28 squared divided by a radius of 11. Whoop, I got divide in there again. All right, so we got a centripetal force of 64 newtons for the first one. If I double the radius and keep the speed the same, that number should come out to not 64, but half of that, 32, right? So we'll check. 0.9 times 28 squared, so I'm keeping the speed the same, divided now by 22, okay, 32. So we know that there's an inversely linear relationship, okay, between radius and centripetal force. Bigger the radius, smaller the centripetal force. Okay, now we talked about this the other day as well. Okay, if we take an unbanked corner and we negotiate it, we're keeping in that corner due to friction. Okay, friction is what holds us in there. So as we go around the corner here, okay, static frictional force, because we're not sliding, okay, helps us to negotiate the corner and pushes us back towards the center of the circle at all points. Everybody okay with that? If it's slippery, then we start to slide out of the corner. Now, if we've got like an infinite amount of room, is there a point where, you know, if we're kind of doing that corner, we might actually start to arc back in? Okay, there probably would be. So I would travel, you know, I try to go around this corner, but it's icy, so I start doing this. But okay, I would probably at some point start to arc back in, okay, because I would eventually reach that point where the amount of friction the ice could provide would be enough for me to turn. The difference would be that the radius of my turn would be much bigger because I have less centripetal force available to me, right? So when I'm going around an icy corner, I have two choices. Slow down, smart choice, Okay, take the corner wider. Maybe not possible. Okay, drifting not an option. Okay, to set up the drift would require you to have at least some friction available. Okay, and it would be hard to swing the end around and get the back wheels doing anything for you. Okay, without any friction. All right. Again, they can spin all they want. If there isn't any friction, they don't do anything, right? Well, well, not on ice it doesn't. And on ice it just looks like a car going in a straight line towards whatever happens to be in the way in that straight line. All right. So here's the challenge in the whole circular motion unit. Figuring out what's providing the centripetal force. Because every one of these questions is going to set up as a sum of all forces problem. Okay, so really it's going to be that FC, which is our net force, is equal to whatever force is pushing us back towards the middle. So in the case of an unbanked corner, that would be the force of friction. Okay, so since we know that, then we can say that mv squared over r, m times a, equals the sum of all forces. So that would be, mu times the normal force. Okay, this is what basically all of our problems will come down to in this unit. Centripetal force is set equal to whatever force is providing the centripetal force. Okay, in this case, it's friction. Now, because this corner is not banked, it's level. What's Fn? Be equal to what force? Gravity, right? So really, this would be mu mg, right? So in this question, I know that we're going to compare the speeds at which a car can safely negotiate an unbanked corner that has a radius of 50 meters in dry weather, where the coefficient of friction is 0.9, versus icy weather, where the coefficient of friction is 0.1. Right, so we're going to compare the speeds at which we can take this same corner. Right, this picture here is just showing somebody doing essentially the skid pad test, which is what all car manufacturers use to test the cornering ability of a car. They have a circle of set radius, and they drive the car around that circle faster and faster and faster until it skids out. Okay, whatever the maximum speed it was before it skidded out is, okay, they can compare that to other vehicles and say, well, this car corners well, or this car doesn't corner well. So if you're driving like a big cube van, okay, it's not going to be very good, okay. Whereas if you're driving like something very small, low to the ground with all-wheel drive, probably a lot better. Okay. All right. So for this situation, okay, we're going to calculate what the speed is. So I want to get speed by itself. So what do I have to do with R? I'm dividing by R. If I want to move it, I should multiply. All right, so I'm going to multiply both sides by R. Okay, and then what do I have to do with M? Divide. Well, actually, there's an M on both sides. What will happen to them? They'll cancel. Right. Okay, and this is actually kind of important. When they show you a speed limit for a corner, they just show you one, right? Do lots of different cars take that corner? And they all have different masses. But for that corner, the speed is set. Mass doesn't matter. Okay? They have to be able to set it that way. Otherwise, they'd have to have like 100 different signs on every corner. If your weight is between this, take the corner at this speed. If your weight's between this, take the corner at this speed. People would just go off the road because they'd be trying to find which speed they're supposed to go. Okay? Wouldn't make any sense. All right, so what we end up with here, guys, is that V is going to equal the square root of mu times G times R, or Muger. You'd be surprised how often in this unit that will be your formula. V equals the square root of Muger. It happens all the time. Okay. All right. So now we're going to calculate how fast the car can take this 50-meter corner under ideal conditions. So mu is 0.9 times 9.81 times the radius, which was 50 meters. Okay, so square root of 0.9 times 9.81 times 50 meters. All right, so under ideal conditions, the car can take this corner at 21 meters per second, okay, which is fairly fast. Okay? 75 kilometers an hour, right? It's only a 50-meter corner. It's about the same as the track out there. Okay. Now we want to do the same thing for when it's icy. When it's icy, we have 1/9 the amount of friction. Okay. Coefficient of friction in dry is 0.9, in icy it's 0.1. So we have 1/9 the available friction for this. Okay, it's still going to be Fc equals the force of friction. Okay, but now V is going to equal the square root of 0.1 times 9.81 times 50. So how much slower will we have to go if we have 1/9 the friction? So we have 1/9 the friction. But remember that the formula says speed and force are exponentially related. I have 1/9 as much friction, so I will only be able to go 1/3 as fast. Okay, square root of 1/9 is 1/3. Okay. All right. So when we do this, and we plug this in, 0.1 times 9.81 times 50. Okay, 7. Exactly 1/3 of 21. Okay, so we have to go 3 times slower, essentially. Okay, because of the reduced friction. Making some sense? Okay, so the big thing to remember here, guys, is our challenge in this unit is similar to what it was in the last unit. Identify the forces involved. This time there won't be as many, and they won't be as vector related. Okay, what is keeping the car in this, or what the object, whatever happens to be, what is keeping it in the circle? Once you identify that, that is your centripetal force. Fc will equal that force, right? And then you'll just set the formulas equal to each other. Okay, questions there? All right, so we did that. And we did that one too. All right, banked curves. So in NASCAR racing, they have these really, really steep corners, okay, that they can go around. Now, the reason we bank a corner is so that we can get additional centripetal force acting towards the middle of the circle, or to guarantee a force acting towards the center of the circle regardless of the road conditions. That's probably the most important part. Okay, so we bank corners, okay, because they help us to have more safety on the road. Okay, they also allow us to make interchanges tighter. They save space. Okay, if I don't bank, like out here when we're going on to Highway 2, okay, if I don't bank that corner and it's just flat, then I have to make the speed limit not, what is it, 60? I don't even remember. I just always go around it. Take it so often, don't even think about it. Instead of being, let's say, 60, it might have to be 30. And it would be far more dangerous in the winter, because in the winter, if there's a lot of ice or snow on it, then even at 30, it might not be safe to take, right? I might have to slow down right to 10 because I don't have the bank pushing me back towards the middle. Right? So essentially, what we have in a banked curve is an inclined plane. Okay, but it's an inclined plane that is a corner. Wow, I should take a snapshot of that. That's like my best drawing ever. It's like perspective and 3-dimensional and the whole works. Okay, so we've got this corner like this. Okay, if I have an object sitting on this or going around this corner, okay, there's the force of gravity pulling it down. Okay, same as always with any inclined plane. And there's the normal force pushing back up. That's if it's just sitting there. If I'm going around this corner, do I have some inertia pushing me into that corner? So what does the corner have to do then? It has to push back. So what ends up happening when you're doing this as a corner, and rather than just an inclined plane, is actually that the normal force gets bigger. Okay, so what we have, okay, is the triangle changes a little bit, and we have this normal force that's big. Okay, we have gravity here, and then we have this force here. Okay, so it's no longer like F parallel anymore. This is now pointed back towards the center of the circle. and it acts as a centripetal force. Okay, so this side ends up being F normal, this side ends up being Fg, okay, and our resultant ends up being the centripetal force back to the middle. You're never going to be asked to derive that triangle. I'm just explaining to you where it comes from. Okay. All right, so the steeper we bank this, okay, so if I make this bank steeper and steeper and steeper, this triangle alters. And FC gets bigger the more I bank the corner. Everybody kind of follow me there? Okay, the more I bank the corner, the bigger FC will get. Now, there's a problem with that, though, okay, in that if I make this really, really steep, okay, from an inclined plane perspective, this triangle is also still there, okay? If I make this too steep, then if I don't go fast enough, I will slide into the middle of it, okay? And that's actually the problem with the NASCAR corners, okay? You have to go a certain speed around those corners or you'll actually slide off of them or into them, okay? This is why I was telling you before, when they actually pave those corners, they put the paver on there, but the paver is tall, so it has to be held on with a crane from outside the track. So a crane pushes it or pulls it into the corner and keeps it there so that it won't slide down as it's paving the corner. Okay. All right, planes do the same thing. If you've ever been on a plane, okay, if a plane wants to turn, it doesn't just turn the rudder, okay, that's the little thing on the tail, okay. I mean, it can do that for small course corrections, but if it needs to make a big turn, then it will tilt its wings, it'll bank, okay, and as a result, some of the lift produced by the wings, okay, it angles, and so some of it is directed back, the horizontal component is directed back towards the center of the circle. Now, there's one problem with banking a plane, okay? And that is that when you bank the plane, okay, when it's flying level, the lift produced by the wings offsets the force of gravity. But as soon as you bank the plane, gravity will be greater than the lift, and the plane will start to what? It'll descend. That's why planes do this when they're approaching the airport. Okay, you've probably noticed sometimes when you're about to land that the plane flies in circles a little bit. Okay, that's to lose altitude, right? It banks the wings, and that allows it to slowly lose altitude, okay, around the airport. Okay, that's what they have to do. If they're in a holding pattern, they have to do that. Okay, if they're coming in right on time, then they get the long, nice glide path straight in. Okay, but if there's anything going on, which there almost always is, okay, then they circle for a bit, and the circling will eventually bring them back down. Okay. It's something that fighter pilots do have to be aware of when they're making high-speed maneuvers and things like that, and they're making turns, okay, during a dogfight. They know as soon as they bank their wings, they're also going to drop. Okay, so they have to be aware of that. And if they're the attacking aircraft, they have to anticipate that when it turns, it's going to drop. If they don't, they'll shoot and miss. Okay, all these things have to be taken into account. They just put more power on. Yeah, if they put more power on an angled, like fighter aircraft actually have two sets of, like they've got the kind of front wings and then they have the small ones at the back. So they can use their rudder as well as that to produce enough lift to go up in a circle as well. I'm saying that in a non-powered loop, they would descend. In a powered loop, they could ascend as well. Okay. Okay, so this was, oh, I should have just shown you this diagram. It's way better than the one I drew. Anyway, okay, so what we have here, guys, is that we have this going on. The car is going around the corner, so normal force now becomes the hypotenuse of this triangle. Okay, this side here is offsetting gravity. Okay, and this side here is acting as our centripetal force. Okay, everybody all right with that idea? So the forces involved here are gravity and centripetal force. Gravity is the adjacent side to the angle, and centripetal force would be the opposite side, would be up here. Okay, it would be the opposite side to this angle of bank right here. Right, so this is what like road designers, interchange builders have to do. Okay, when they're designing the interchange and they want to build the corners, they know how much room they have, so they know the radius of the corner. That's kind of set for them. Okay, so what they have to do is bank the corner for a reasonable speed. Right? So they use the same formula that we're going to derive here in order to do that. Okay, so this angle here, okay, so theta, okay, like we said, is going to be related to the opposite side and the adjacent side. Everybody okay with that? Okay, what trig function relates opposite and adjacent? Tan. All right. So we're saying then that the tan of theta equals the force of gravity, sorry, the adjacent side, centripetal force, over the force of gravity. Okay, that's what we're saying. How do I calculate these two forces? Well, then I can put in their formulas. Okay, I can say that the tan of theta equals mv squared over r times mg. Okay, this is saying Fc, mv squared over r, divided by gravity, mg. What happens to the m's? They're going to cancel. Okay, there's our bank curve formula. The tan of theta equals v squared divided by r times g. So this is the formula that a road planner would have to use to calculate their banking angle for the curve. Okay, so they would know what r is because, again, the space is set. They know how big a corner they can make. Okay, they would probably decide on the angle of bank and determine then the safe speed, or say I want this corner to be for 40 kilometers an hour, calculate the angle of bank and build it that way. Okay, so that's the formula that they would use. Now, let's go back to what canceled here. What canceled? Mass. Important or not important? Very important. Otherwise, again, every corner needs 100 signs, okay, to account for all the different masses of vehicles that might possibly take that corner. Okay, the angle of bank is independent of the mass. It doesn't make any difference, right? We're not relying on friction to hold us in a bank corner, so mass no longer matters.
What force is keeping when you do the olive up, you spin it around and upside down, the olive?
Same thing. Yeah, same thing. So if you spin it fast enough, it's basically just a uniform circle, okay? It's because it's horizontal. So as long as you get it going fast enough, it'll push against the side of the glass will push it back to the middle. And it is a bank curve because it's a cone, right? But yeah, that's basically the same idea. All right, we'll leave it at that and we'll work on some problem solving stuff tomorrow. No quiz tomorrow because we just haven't done enough stuff yet, okay? But there will be some next week for sure.